Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day, here in my virtual classroom. Step on inside. Big Ideas Math, Integrated Math 2 textbook, Chapter 11, on circumference, area, and volume. We are doing the review of this portion in the textbook. 34 questions in total, with examples leading into each individual section. If you haven't seen the individual sections in the videos I covered, you can check them out in the playlist featured in my description section below. But if you want to follow alongside this, I have the PDF for this down in the description section, as well as timestamps to each individual problem or each individual section. You're going to want a calculator for this as well if you want to follow along and make sure you're doing things the right way as well. Let's go ahead and get started in 3, 2, 1, and go. Okay, we are going to start with section 11.1 on circumference and arc length. By the way, sorry if I sound congested. It's been like a chronic 2-month allergy fest for some reason, and I can't get rid of it, so apologies. I'm going to have to fix it sometime during the summer, apparently. Anyway, circumference and arc length on this. The arc, here's an example. The arc length of QR, is 6.54 feet as labeled. Find the radius of circle P. Generally in problems like these, what you're looking to do, and they're doing the same thing here, is, there's a proportionality here. Whatever this central angle is out of the full 360, this arc length is out of the full circumference. And that's what they're setting up here. 2 pi r being the circumference. You can either find the circumference and then find radius after that, or just use that part of the formula there and solve for r. So the arc length of QR is 6.54 feet. The measure of arc QR is 75 degrees. Remember, 75 out of 360 is whatever that ratio is. This will stay in that proportion. Looks like they would go to cross multiply and divide both sides by 2 pi. You get a radius of about 5 feet, and that ends up being the answer. So I'm sure we're going to see problems like that. If not, we probably definitely will in the next section on areas of sectors and things like that when it comes to proportions. So get ready for any of that involved. Let's start with number 1. They want to find the diameter of circle P given an arc length. Oh, that's not an arc length. That is the whole circumference. I actually don't need to do the proportion for this one. The circumference is, I don't need the diagram really, 94.24 feet. And, you can use diameter times pi as circumference formula. So 94.24, the circumference equals diameter times pi. If I divide both sides by pi, I get the diameter. And I don't know if this is going to come out cleanly, just like that other problem is. I think, for the most part, they kind of imagine that it will. But we're going to go ahead and calculate it and round this. They did to the nearest hundredth, so we'll do to the nearest hundredth as well. I'm going to jump to my calculator and just try this without showing you on the screen. 94.24 divided by pi. And I'm getting, so it says 29. Let me actually show you this. It shows 29.9975, etc. So they're clearly wanting to try and round that to 30, and that's going to. So about 30 feet, and that's going to be the diameter for this guy for number 1. And that's it. So no proportionality really needed on that one, because we don't have an arc length to work off of to get the circumference, therefore diameter. But there's that. Number 2 seems like it is that kind of problem, though. So on question number 2, we need the circumference of circle F, just C, given all the information we have here. Now, 35 degrees out of the 360 is whatever proportionality we can use to equate this arc length of 5.5 centimeters out of the entire circumference. Okay, so this isn't quite 30. Let's say it was 30 for a second. That would be a 12th. So this would be a 12th of the whole thing if that's the case, and we could use that. I mean, this stuff here, we can do what they did before without even reducing the fraction. You can cross multiply, because ultimately, I'm not going to write the answer as a fraction anyway. I can just write it kind of like they did here. Divide by 35 afterward. I always multiplied by reciprocals. I was doing more of that in my videos earlier. But this is 5.5 times 360 divided by 35. I mean, ultimately, I got to do those calculations anyway. Let's just work it out like that. It's pi is already a part of the answer. In terms of 2 pi r or diameter times pi, it's just a part of the circumference. So I'm just going to work this out what it is. It'll be some exact answer of some sort, and we'll figure it out. Times 360 divided by 35. And I'm getting, it's not exact. It's rational, but it's got some decimal work. So it's about 56.57 centimeters. And I believe the answer, because 35 is just a little less than a tenth of 360, and 5.5 is a little less than a tenth of that number. So I'm believing my calculation that I got it right. Number 3, we're going to find the arc length of arc AB. This time we're given the radius. So given that the radius is 13 inches, I'm going to start off with that. Let's just go straight into circumference talk. And then we can calculate everything off of that. Circumference is 2 pi times your radius. That'll be 26 pi inches. Now, I could round it, but I'm going to use this calculation in a future answer. So let's do what we did before. What 115 degrees is out of 360. The arc length AB, and I'll just call it x for now. I'm even going to put an x here to help you. The arc length of AB is out of the circumference of the circle, which is 26 pi. So if I multiply both sides by 26 pi, that'll be, x's answer. 115 over 360 times 26 pi. And I wish the 115 over, I can reduce it, but I wish it was like a clean reduction that I could say, oh, it's like 4/7. I don't think it's quite as clean as that. So let's just go straight into that. And like I said, we're going to do the rounding such and such, so we might as well already, put the pi in it and such. Hold on, I typed it wrong. Not 15, 115 times 26 pi. Okay, so there's probably an exact answer version in terms of pi. I'm going straight into this. It's 26.09. 26.09 inches. And yeah, we do need units for these ones, y'all. All right, that's 1 through 3. Let's look at number 4. Mountain bike tire has a diameter of 26 inches. To the nearest foot, how far does the tire travel when it makes 32 revolutions? So every revolution is the entire circumference of that tire working itself out. So if a mountain bike has a diameter of 26 inches, then we got to work out its circumference, which is diameter times pi. 26 pi, once again, just like this previous one. How far does it travel when it makes 32 revolutions? You have to remember we're still in inches right now, by the way. We'll go into feet ultimately by dividing everything by 12. But let's figure out the 32 revolutions thing. Now, I'll set this one up as a proportion as well to make sense of it. One revolution, and you can write this different ways when it comes to your proportions. I can say one revolution is to 26 pi inches as 32 revolutions. Actually, let's do it the other way. 26 pi inches is to 1 revolution, as this unknown amount of inches is to 32 revolutions. What's ultimately going to happen in this proportion is we're going to multiply by 32. See, I multiply both sides by 32 now. It goes by itself. X is 26 pi times 32. Now, I'm going to keep the exact answer for a moment because I still haven't rounded to feet. So I'm going to just do 32 times 26 for a moment. And I get 832. So this is 832 pi inches. Whatever that is when you multiply by pi is whatever. Close to 2,500, a little more than that. Let's figure out how many feet that is. So now I'm going to multiply by pi. Let's do this as a proportion. 12 inch. Let's see. I want to do feet ultimately, right? So 1 foot is to 12 inches, as how many feet is to 832 pi inches? Ultimately, what do? We multiply by 832 pi, but ultimately we divide that by 12. And I'm saying these things in a way that you probably know to do that, but in case you don't, I'm showing you how the proportions work out in every sense. What we did here and here is the same stuff that we were doing up top. There's the same proportionality involved. So yes, you divide by 12 to get to the feet. So this is in feet, and I'm going to actually do that division. Remember, pi is a part of it. So times pi divided by 12. I did no early rounding because I had other calculations to be had there. And when pi is involved, we're just going to get something irrational looking. 217.82 feet. Sounds good. So this tire with that diameter would travel this far after rotating 32 times around, because the circumference is the amount that it travels every time it covers a revolution. All right, that is section 11.1. Let's go to 11.2 on areas of circles and sectors. Before we hit numbers 5 through 7, let's see what they show here. It should look very similar to what they had previously. Actually, before I do that, I see what they're doing here, and I want to write it out in a different way. Find the area of sector ADB. That's what's in blue. Literally, as I draw it in blue, that's what's in blue right there. They're not showing the proportionality, but I want to show it in the exact same way as before. Let's say that this was X. X was that area. What they don't show is the step before of proportionality. Whatever the 80 degrees is measure the arc. So whatever 80 degrees is out of 360, the area of the sector is out of the area of the entire circle. Pi times r squared. Notice that from here, they're going to multiply both sides by this thing, and then you'll have x equals 80 over 360 times that pi r squared. So they are here without showing why they're there, and I'm not saying you have to write the proportion for it. You're taking literally 83/60ths of that amount, of that area, but that's what we were doing the whole time before. So to show something different is, I just want to make sure you know where it's coming from. So in case we show it like that too, just be ready. Anyway, they calculate that. They get 69.81 square meters. This congestion, man. Let me kind of take care of this for a second. Unfortunately, I don't think I can beat the congestion game. Okay, let's jump to number 5. I mean, I'm as annoyed with it as you are, I'm sure. Find the area of the blue shaded region on number 5. Now, they show the arc of TW. Let's say, I'll write this out. Measure of arc TWU is 240 degrees. Now, this one's nice as a number that can clean up later. Whatever 240 is out of 360, which is a very clean number. The area of my sector, again, I'm going to call these X whenever I can. This X is out of the area of your circle, the entire circle, which would be pi times 9 squared, 81 pi. Now, I'm going to clean this up in a couple ways. Pi times 9 squared is 81 pi. That's the area of the entire circle. And 240 over 360, we can divide this both by 120. That's 2/3. X is 2/3 of 81 pi. We are going to take 2/3 of 81 pi. We multiply both sides by 81 pi, and we get that. As an exact answer, that's 54 pi. As rounded to the nearest whatever when you multiply by pi, I don't know, 170 something? 54 pi, 169.646. So 169.65. This is in, what was it, in inches? Square inches. This is a square inch unit value for number 5. All right. Number 6. 6 looks a little bit different. It's more of a composite region that's comprised of a rectangle and taking away a semicircle from it. So if we find the area of the rectangle, so I'm going to do less of the, here's the thing, a semicircle is literally half the area. Just like this was 2/3 of this area, semicircle's half. I'm not even going to set up a proportion for that. Whatever the area of the rectangle is, we'll subtract the semicircle as area out, and boom, we've got it. So I'm just going to say the area of the shaded, let's start with this. Area of the shaded equals area of the rectangle minus area of the semicircle, like that. So the area of the rectangle is base times height, length times width, whatever you want to call it. 6 times 4. 6 times 4, you get 24 square inches. You're going to get used to the volume stuff when we do them by me breaking this stuff down like this quite a bit. The area of the semicircle, here's the thing. The diameter is 4 because this guy's 4, so is this. Therefore, the radius is 2. See, I can't use diameter in my formula. I got to use radius for it. It's pi r squared. So pi r squared, pi times 2 squared, 4 pi. 4 pi square inches. I don't dare. Oh, I'm sorry. That's the circle. The semicircle is going to be half of this. 1/2 of this. I was going to say, I don't dare round something early, but this is the only number that's going to be rounded ultimately. I could. I just want to kind of write it in full to begin with. So 2 pi square inches for the semicircle. Half of the area of the whole circle. Okay, so the area of the shaded, therefore, we're going to take 24 minus 2 pi. That results in square inches. That's an exact answer, not a very favorable one, so we'll go ahead and round it. So it's going to be 17 point something, I guess. Minus 2 pi. 17.716, so 17.72. 17.72 square inches. All right. All right, that's number 6. On to number 7. They want the area of the blue shaded region, knowing the area of the red shaded region is 27.93 square feet. We hadn't really hit a problem like this before. We'd done some before where we had to find both blue and red. From here, what I would do, well, it's interesting. There's more than one way to go about this problem, I'd say. Here's what I'm going to do. I'm going to take, oh, that's just the shaded region. That's not the sector. Okay. Okay, well, let's just start setting up proportions and see where we go from there. The area of the shaded region that I'll call X for now. I'll call this one X, I'll call the other one Y. The area of the red shaded region X is a fraction of the entire circle, right? So whatever 50 out of 360 is, actually, let's do this. Let's do this. This is going to be a little bit different. If that's 50 degrees, because what I was going to do is I was going to get the radius, use that to get the area of the hole or set up the proportion. I don't think I need to do that. What I could do is if that's 50 degrees, this entire part is 310 degrees, right? The rest of what makes that circle. So 50 degrees, I'm going to do it this way. I'm not going to do degree over degree. I'm going to say 50 degrees is to the area of the red region, 27.93 square feet, right? Those are in proportion with each other, just as 310 degrees is to the area of the blue. I'll just call that Y. The area of the blue portion of the region. I skip by the radius completely by doing this. I don't need the area of the entire circle. They just want the area of the blue. Let's do that. Let's do that. Now, I didn't have to write it that way. I could have done 50 over 310. I just wanted to just make sure that you understood 50 goes to this part, 310 goes to this part. I probably could have swapped things around. I'm going to multiply both sides by Y. This is kind of how I did things in the previous sections, probably this section at the time. Multiply both sides by Y. Multiply both sides by the reciprocal here. This is where you get 27.93 over 50. 27.93 over 50, right? That's multiplying by the 310. So that's where we get Y by itself. This is where I'm going to do some of my rounding biz. Now, this number was already rounded. There's nothing I can do about that. Divided by 50 times 310. I get 173.166. It feels kind of icky to round here, given that they give me only 3 decimals and such, because I can't really claim that to be exact, given that the other one's probably approximate. But I'm just going to go ahead and write it like that. Anyway, that's in square feet. That should be the answer. There are multiple ways to do this problem, and that was the way that I chose. So it works. Okay, let's move on to areas of polygons. Where do we want to go from here? Well, let's start with, this is a two-parter of an example to see what we can talk about. Oh yeah, we did kites and rhombuses as well as, excuse me, the regular polygons. So they jump straight into regular polygon talk, which is probably wise. There's more to be had here. I can talk about the kites and rhombuses just with a single formula. This has a single formula, but there's more to do. A regular hexagon is inscribed in circle H. Find the measure of arc EHG, this guy, and that's one that we use a lot, all the time, and the area of the hexagon. We probably use this angle to find it, so get ready. So they first start by talking about a central angle, this guy here. It goes from radius to radius. That's where you find a central angle. They are congruent to each other. You have congruent isosceles triangles in here, and there are 6 of them in a hexagon because it's a 6-sided shape. So the central angle, you take 360 and divide by 6. You get 60 degrees. So the whole thing's 60 degrees. Now, HG, the apothem, is also a bisector of that angle, which means it'll divide it into 2 congruent parts. That makes one of them 30 degrees. So the one they were trying to find, this GHE or whatever they call it, is 30 degrees there. Now, this one is more particular than some other ones because this is in a special right triangle. It's in a 30, 60, 90. They even call it out as such. In other cases, we're going to have to use trig. Here, we can use the 30, 60, 90 ratio relationship, where in this right triangle, 16 is the hypotenuse. Opposite the 30 degree angle would be 8 right here, and then the apothem would be 8 root 3. And these are important values that we need. Apothem's a part of your formula, and the perimeter of your hexagon is part of your formula. Since I said that this thing, the apothem bisected the central angle, it also bisects one of the side lengths, and all the side lengths are congruent in the regular hexagon. So if this is 8, we can double it for 16. That's what they're showing you here, the length of a single side. And then the perimeter, therefore, is 16 times 6. 16 times 6 they're going to do to get the entire perimeter. They write it as n times s. That's the number of sides times the length of each side. That's also the perimeter, because the area of your regular hexagon is 1/2 apothem times perimeter. That's what I'm going to be writing each time there. So 8 root 3 is the apothem. It's the distance from center to the shortest length to any of the sides, 8 root 3. Based off the 30, 60, 90 triangle ratio relationship. We'll be using trig a lot as well. Well, I'm not going to say a lot. This is a quick review, but I have in the past. 8 root 3 times the perimeter, that's actually 96. So half of apothem times perimeter will give you approximately 665.1, and it looks like they're using 1 decimal place, so I will use 1 decimal place as well. And that's just in square units. They didn't have any units for it. So they found both things. The central angle, excuse me, not the central angle. The mini angle they found here was 30 degrees. That was totally used in our values to find other things. And then we continued forward. Now, numbers 8, 9, and 10 are not regular polygons. So these are a little bit different, but they are kites and rhombuses that have the same formula basis. The area of a kite or area of a rhombus can be found in the same way given that you are referring to their diagonals. As they're always perpendicular to each other, you take half the product of both of your diagonals. So if you can find their diagonal's length, and there are properties of kites and rhombuses that we might have to work with to find them, then we can use those there. And they clearly set it up that way. They didn't draw the perpendicular portions here, but that's what kites and rhombuses do. They have perpendicularity among their diagonals, which makes that work. So we might have to use Pythagorean theorem things. I don't really know. We'll figure it out. Let's start with number 8 on this kite. This kite has a length here of 13, which means that this diagonal here is 13, right? Right? And then 20 is the length of the other diagonal. So straight up, the area of that kite is going to be 1/2 diameter 1, let's call it 13, times diameter 2 of 20. Half of 20 is 10, and 10 times 13 is 130. We get 130 square units there. And I will put u squared for that. It's exact. No in terms of pi stuff for now. Number 9 is a rhombus. It shows all 4 congruent sides, and they're broken up into 6 and 6, 8 and 8. 6 plus 6 is 12. 8 plus 8 is 16. Area is half of 12 times 16. Half of 16 is 8. 8 times 12 is 96. I don't want to get that wrong. I think so. So we get 96 square units for the area that are rhombus. And number 10 is a kite. Once again, they're giving you those lengths. Same thing when it comes to sum. We got 7 plus 7 and 3 plus 12. So 14 and 15 as your diagonal lengths. They get pretty basic. They didn't go off any Pythagorean theorem stuff. So half of 14 times 15. Half of 14 is 7, and 7 times 15 is 105. So 105 square units for that one. So like I said, stuck to basic. We will accept basic as we move forward to the next set. Because I'm not even a third of the way through all my problems. And that's a problem. All right. Find the area of the regular polygon. Now, they give us a hexagon again to play with. I won't copy and paste it per se. What I'm going to do is just draw just the bottom portion of it to work out the parts that I need to work out. They have a side length of 8.8. Now, I'm going to draw this center. Imagine that the hexagon was completed. I'm going to draw the center and this apothem, which we still need to find. We need to find the apothem length. And, you know, our area formula is 1/2 apothem times perimeter. That's why we need it. Perimeter I can find straight off the bat. It's a hexagon. Each side length is 8.8. We'll get to that. Let's get to the apothem talk by figuring out, and we just saw it, but this angle here, based off the central angle. The central angle, the whole thing, is 360 over 6, which is 60 degrees. Therefore, half of that is 30 degrees. This is what we need here. This is a right angle of a 30, 60, 90 triangle. Now, the other part is this 8.8 got bisected, divided into 2 parts. That makes this 4.4, half of 8.8. 30 is, or 4.4 is opposite the 30 degree angle, the shortest side. The apothem is going to be root 3 times larger in a 30, 60, 90 triangle. It'll be 4.4 root 3 units long. Now, the perimeter is the other part we need to find. There are 6 sides, each of length 8.8. 8.8 times 6 is some exact value. Is that 52.8? 8.8. 8.8 times 6. 52.8. 52.8. So the area of this whole thing is 1/2 apothem times perimeter. And I could spend time giving you an exact version of an answer, but it'll have decimals with the radical. I might as well go straight into it. They did round to the nearest 10th last time, so I'm going to go ahead and do that as well. 4.4 root 3, and I'll divide it by 2, taking half of that. All right, 201.195. I'm going to call that, oh wait, they round to the nearest 10th. 201.2 square units. Okay, that's number 11. Let me sniffle myself out. Well, I tried, and I believe I failed. Okay, number 12. This is a, 1, 2, 3, 4, 5, 6, 7, 8, nonagon. It's a 9-sided shape, so let's start with that. We have an n value, I'll just call it n value of 9. Let's work off that perimeter right now while we're here. 5.2 times 9 is what we're working with. I can do that in my head. I got it. 46.8, 46.8. If I'm wrong, uh-oh. I'll check it later. 46.8 units. That's what the U is for. Now, in this nonagon, listen, I'm going to do the same kind of drawings I did before. It's not meant to be exact. It's meant to work off what we have. What they give you here is the radius of 7.6. That's this right there, 7.6 units. The 5.2 can be used as well. I don't know if well, they sure have to be pretty exacting what they're going to show here, because if they show me a 5.2, and they did not need to show me that. They only need to show me one length. If they show me the 5.2, oh, you know why they probably show it? No, that works. Here's the thing. They're showing me too much. You know, if this is 5.2, what's half of that? 2.6, right? So I have two ways I can find apothem. And listen, I'll show you both of them. There are two ways we can find apothem. One way is Pythagorean theorem, where we can say a squared plus 2.6 squared equals 7.6 squared, right? It's a Pythagorean theorem thing. We can work that out, and I'm going to. Let's do that first. So because I want to see which, like what they kind of look like. So 7.6 squared is 57.76. Listen, I'm going to subtract the 2.6 squared already. I'm just going to kind of get into it. 2.6 squared. Oh, 51. Okay, that's an exact value. So a squared is 51, so a is the square root of 51. Okay. I'm kind of liking that one as far as what to use, because here's the other way we can do this. And I guess it should work the same way. I'm going to see how the numbers compare in a second. The other way is using trig. And we have options on what you can use with trig. The way to use trig on this is we can get the central angle measure, or this angle measure, not only by arc sine of this stuff, but we know that the central angle for the entire thing is 40 degrees. So this will be 20 degrees. So I have multiple ways that I can find apothem based on that. And I'm going to try them all. I'm going to see which ones kind of work best. We can use cosine. We can say the cosine of 20 degrees is a over 7.6. Therefore, a is 7.6 times the cosine of 20. The real question is, these numbers got to be rounded from something, because cosine of 20 is an irrational value. Which one is most accurate to root 51? I feel like that's the one I kind of got to use. But we'll see how these work. We can also use tangent. The tangent of 20 degrees is 2.6 over a. Switch these places, you get a is 2.6 over tangent of 20. So I'm going to go to the calculator, and I'm going to write all three of these things out. I got this, and probably what I'm going to use in blue. But I'm showing all the different versions, and why they showed us too much information. I wish they didn't show us all that, because now I'm conflicted with what I should use. I feel like square root of 51 should be best, especially because that was like exact as an integer. So let's see how these work. First, square root of 51. All right, so it's this number here, right? And remember, we don't round anything early. Whatever I use here is that. Now, what's 7.6? Be in degrees. Yep. What's 7.6 times the cosine of 20? It's going to be close. It must be, right? Pretty close. At least to the nearest thousandth, it's pretty close. And what's 2.6 divided by tangent of 20? Now, as good problem writers, all these should be pretty close to each other. So that one's a little bit more off the mark, but you can see there's rounding to be had. This is why we don't use numbers and round early with them, because it can influence and change your values very much. This one must be the best one to be working off of. I feel like Pythagorean theorem was the way to go, so we're going to go ahead and do that. So I'm going to use the square root of 51. So we have the perimeter, we have the apothem. So we're going to say area. Sorry, I was pointing to them. You didn't see my mouse. But area is 1/2 of apothem times perimeter. Like that. Okay, anyway, a lot of excess work for things we didn't end up using. I hope that's okay that we just talk about how we can do them in different ways. And let's go ahead and compute that. So I got square root of 51 times 46.8. And I should have checked that that was right, but all divided by 2. And I'm getting 167.1, about 167.1 square units for the area of the regular nonagon. Okay, so let's move on to number 13. I feel like they're doing the same thing to me again. Because last time we used Pythagorean theorem, I guess I'm going to do it again. But they're giving you more information than we need. We know it's a pentagon, So we could find, and we did a lot of, for our problems, guys, we did a lot of pentagons. It's to the point, I know now this is 36 degrees. I don't even have to think about the calculation. I know it's 36. I'm going to stave off using the 36. You can, but you can see where there's some rounding error. So let's just use what they have. We got to basically find the perimeter. We have the apothem. The apothem is 3.3 units. The perimeter is based off a side length. Now, if I call this half a side length x, like that, x squared plus 3.3 squared is 4 squared. X squared plus 3.3 squared is 4 squared. I don't know if this is part of like a Pythagorean triple set. This is going to be a beautiful looking number. I know that number is 16, but I don't know what happens when you subtract 3.3 squared from it. So let's see. 5.11, 5.11. So x squared is 5.11. So x is the square root of 5.11. I don't dare. Well, let's see if it cleans up. I don't think it does. I don't think that's a perfect square value. Definitely not. So square root of 5.11 is just x, right? It's just that part. Listen, the perimeter, there are 5 sides, and we have to double 5.11 for that. I'm kind of going the fast track on that because 5.11 is half of a side length. So that's going to be 10 root 5.11. There's my perimeter. Not using trig, using Pythagorean theorem. I mean, it's interesting that they gave us more than enough information twice. And we didn't really get to practice the trig on it. I showed you it from the last problem, but we didn't get to get official practice. But whatever. Anyway, the area is going to be 1/2 of dat apothem times dat, this was in units by the way, times dat perimeter. And rounding will be had to the nearest tenth, as it seemed they did in the example. So 3.3 times 10. Let me just write a 5 because I got to take half of it. 5 root 5.11, and I get about 37.3. 37.3 square units for that area. Okay. All right, let's move on to number 14. Oh, okay. We have possibly another area question here. A platter is in the shape of a regular octagon with an apothem of 6 inches. Find the area of the platter. All right, I think this one, I actually get an opportunity to use the trig off of some things. Yeah, I think I get to here. They only give us one bit of information when it comes to length, not multiple. I'm not drawing the whole platter, just drawing out something that can represent what we have. We are given the apothem. The apothem is 6. Now the central angle of this thing, 360 over 8, an octagon, is 45 degrees. So half of that is just this guy here, 22.5 degrees. We're going to work off that. 22.5 degrees. I need to find out this length for the perimeter the same way they did before, only this time I got to use trig. So using trigonometry here, opposite and adjacent of the angle, I'm going to use tangent. The tangent of 22.5 degrees equals x over 6. Multiply both sides by 6. You get 6 times the tangent of 22.5 degrees. Let's keep that exact. Let's double that for the entire side length. And perimeter, it's an octagon, so perimeter is going to be 8 times that amount. 16. Excuse me. I was going to write 16x. 12 times 8. 12 times 8. We just did that. 96. 96 times the tangent of 22.5 degrees. Notice no early rounding. There's your perimeter. We have an apothem of 6. These are inches, by the way. So area being 1/2 apothem times perimeter. I almost feel like I want to do more of an exact answer before I continue forward, but because I want to, I think I will. Half of 96 is 48. I don't know, 6 times 48 should be 288. Let's see, 6 times 40. Oh, wait, yeah, 6 times 48, 288. Okay. So exact answer, 288 times the tangent of 22.5. But if there's one problem to be rounding with, it's a word problem. It just makes more sense. Area of the platter, you don't say 288 times tangent of 22.5 square inches. We actually round it. And we're going to 119.29, so 119.3 square inches. The area of the platter. That's section 11.3. Now, we may use parts of 11.3 and 11.4 when we do volume of prisms and stuff, because we might have to do areas of hexagons for them. In fact, oh, they don't show you on this first one. I thought they were going to do that. But all right, so 11.4, let's go through the example bit. Tell whether the solid is a polyhedron if it is named the polyhedron. Without looking, I can see it's a yes, it's a polyhedron. And specifically, it's a prism. A polyhedron has no curved edges. It's going to have multiple different sets of faces. So a sphere is not a polyhedron. A cylinder is not a polyhedron. A cone is not a polyhedron. Those have circular bases or faces, I should say, or bases. And the sphere has it's like one whole face. So prisms are polyhedrons. Now, how many sides? It is 1, 2, 3, 4, 5, 6, 7, 8. This prism, having congruent parallel bases on top and bottom, forming rectangular lateral faces, is named based off of its bases. Its bases are octagons. This should be an octagonal prism. Let's see what they say. The solid is formed by polygons, so it's a polyhedron. The two bases are congruent octagons, so it is an octagonal prism. Part B, find the volume of the, well, not part B, another problem. Find the volume of the triangular prism. Now, they call it a triangular prism because its bases are triangles, not because they're on top and bottom, but because those are the unique shapes in what would otherwise be all rectangles. So we do find it based off that. Volume is area of base times height. And the area of the base is 1/2 base times height. Its own base and height of its own, like that. They're perpendicular to each other. Height is always perpendicular to base. That is also true of these prisms. Whether upright, whether oblique, is all that. So area of base is 24. That's half of 6 times 8. Times the height of the prism being 5. That's 120 cubic inches of volume of a block of cheese. There it is. All right, let's do our own numbers. We got several. 15 through 17, we start with, for polyhedrons, tell whether it is, if it is, we're not finding volumes. We're just naming the polyhedron. First one, yeah, this is totally a polyhedron. They're not saying why. It has, polygon bases, no circular edges and stuff. It's a square prism, but everything is squared off in such a way, I think everything's the same height, including the heights. I can't guarantee it. They don't show the heights as congruent to me for me to know for sure. I want to call it a cube. It would be a cube if everything was congruent, but does anyone see? I can't tell. I don't see a single marking on any of these to say for sure those are congruent. So now I'm kind of at pause. If I can't see that that's congruent, I can't in all good nature call it a cube, even if it looks like it. I can at best call it a square prism. The bases are squares, possibly rectangles, if not squares, go into the top with height, but I don't know for sure. Number 16 is also a polyhedron. Triangles alongside whatever kind of base that is, which we will count out in a bit. And if it's a polyhedron, we will by extension call it by its name. It is a kind of pyramid. A single base with all triangular faces meeting up to an apex. It has 1, 2, 3, 4, 5, 6, 7 sides. That's called a heptagon. So this is a heptagonal. I don't think I've said this before. A heptagonal pyramid. Very interesting. Yeah, I do not think I've said that before. The 7-sided. We often don't do the ones with 7-sided in general, so there's that. And then number 17, listen, it's not a polyhedron. It says if it is named the polyhedron, it's not a polyhedron, but I still want to name it, just for your guys' sake. It's a cylinder. Now, in some ways, it's not a good official name. In some ways, I call it a circular prism. Because it's not a prism, I don't want to call it that. But it follows the same nature as prisms do when it comes to volume. Area of base times height. The difference is the base is a circle, not a polygon, so we have to do things differently with it. But it follows the same thing, just like cones are kind of like a circular pyramid. All right, numbers 18 through 20, we are going to find the volumes of the solids. We start with a rectangular prism. Every face is a rectangle, so I might as well make the bottom ones the bases and such. So the volume is area of base times height. All right, we're going to do that. So area of base, we separate the work, or I'm going to separate the work. We get length times width, 1.5 times 2.1, which is something that I should probably know. 3.65, 1.5 times 2.1. No, 3.15, darn it. 3.15 square meters. Still got to do the work. The height of the prism is the other guy that we haven't said that separates the bases, the 3.6 meters there. So when we find the volume, we're going to do area of base times height. I don't dare go for... I could probably, if I knew what 3.6 squared was, 1296. I don't think I got it. I could, because this is exactly 7/8 of that. 1290. I can't do it. I can't do it in my head. I'll go. I should have known. But 3.15 times 3.6. Sorry for wasting your time. I'm trying to be clever with it, and it's not working. So 11.34. This is exact. It's 11.34. This is cubic meters. These are cubic units on these ones here. Square units times single one-dimensional units. All right. Yeah, I'm sure you guys don't care about the me trying to calculate stuff in my head. Number 19, we have a cylinder. It's an oblique cylinder, but still a cylinder. The height is the distance between your bases. That's the perpendicular distance between your bases, just like anything else. So it's still 8. So cylinder volume is still area of base times height. The area of the base is pi r squared. Radius is 2. So we got 4 pi square millimeters for area of base. The height is indeed 8 millimeters. No Pythagorean theorem to be had to find some sort of slant height aspect. That's not how this works. So the volume is area of base times height, which is 32 pi square millimeters exactly. It's going to be very close to 100, if not more. So 32 pi, well, yeah, 100 point, I don't know how many decimals they were using. What are they? We didn't get to see. I'll go to 2. I'll err on the side of caution. Probably should have used 2 for the previous set. 100.53 cubic millimeters for volume. And then number 20. Now, number 20 is what I would call a toppled over prism. The base is not this bottom. We don't say, oh, area base is 2 by 4. That's not how it works. The bases are the unique shapes. In these cases, the pentagons. This is a pentagonal prism. Therefore, this is the base. We'll find its area. This is the height of 4. Let's start with that. The height of this thing, number 20, is 4 yards. Don't forget that. Now, the area of the base is going to take a little bit of work. This is one where we have to do the apothem times perimeter stuff. This is where it's used. So the area of the base is 1/2 apothem times perimeter. I'll just write AP. So let's go attack that in this broken up portion of this pentagon. I've said several times the central angle divided by 2 here is 36 degrees. So we're just going to go live off that and work it out. If a length is, oh, perfect. If a length is 2 yards, then half a length is 1 yard. So we'll use this. We got to get the apothem. We got to get A. So we'll use tangent. We can say the tangent of 36 degrees is 1 over A. So A is 1 over tangent of 36 degrees. Like that. So that's the apothem. We got a perimeter of 2 times 5. Pentagon with side lengths of 2 yards each. Oh, this is in yards, and this is in yards. So the area of the base being 1/2 apothem times perimeter. Let's clean that up. Half of 10 is 5, and 5 would go in the numerator here. So 5 over tangent of 36 square yards. So there's the area of the base. Height is 4. So the volume is area of base times height. We have 5 over tangent of 36 times 4, which is 20 over tangent of 36. This is in cubic yards, of course, but that is also, of course, exact, not rounded. Let's figure that out. 20 over tangent of 36. Always hoping I didn't make a mistake somewhere. It's one tiny mistake that'll change everything in the problem, and I just trust that I'm doing everything correctly there. So it's approximately 27.53 cubic yards of pentagonal prismware. Looking good. Okay, that is section 11.4. Several problems. I like how we ended up on that one where we had to use area of volume, area of prism, area of pentagon, area of a regular polygon. Let's go to 11.5 with volumes of pyramids. Not much different from what we did before, although they look different. It takes up 1/3 of the area of what a prism would have been. 1/3 area of base times height. Now, it depends on your base. This base is a triangle. It's a right triangle. So in this example, 1/2 of 5 times 8 is 20. And 20 times 12 well, excuse me, a third of 20 times 12. A third of 12 is 4. 4 times 20 is 80. So we get 80 cubic meters out of this thing. So 1/3 area of base times height. Everything that we did before. Oh, by the way, the height is the perpendicular distance from the base to that apex, no matter how it's drawn. So on number 21, as we start to do examples, let's find this guy. It's a square pyramid. So the volume is 1/3 area of base times height. Area of this base, we got a square 9. We get 81 square feet. That height is 7 feet, and so the volume is going to be 1/3 of those two multiplied. 81 times 7. A third of 81 is 27. 27 times 7 is 189. I don't trust myself. I should. 27 times 7. Yeah, 189. 189 cubic feet, not square feet. 189 cubic feet of volume. Now, you'll notice in 11, 6, and 7, we do surface area of cones and surface area of spheres. We don't do surface area for these ones. I believe it's saved for IM3. I don't know why, but I believe they save it for IM3, if you're curious as to why we're not doing it yet. Number 22, we have a triangular pyramid. I would like to work this one as the height, of course, because you can see that distance going. So the base is going to use that 15 and 8. Area of base is 1/2 base times height. See, these have their own bases and heights within the base itself. The base of the base and the height of the base are here. 1/2 of 8 is 4. 4 times 15 is 60. So we get 60 square yards of base area. This height being 20 yards. The volume is 1/3 area of base times height. Third of 60 is 20. 20 times 20 is 400. You get 400 cubic yards of volume, exactly, for that triangular pyramid. Number 23 is I guess that's a rectangular pyramid. It's still, I don't think it's any harder than these ones. Number 23, we have an area of base of its own base times height. I like to call it length times width in this case. 180 square meters, and the height being 5 meters. So this volume will be 1/3 of 180 times 5. Not trying to trick you. 60 times 5 is 300. So 300 cubic meters of volume. If only the problem sets that they gave us at the time were that easy, we'd be good to go. We still have 2 more problems, though, it looks like. We have the volume of a square pyramid. Okay, this time they give us the volume. So the volume of a square pyramid is 60 cubic inches, and the height is 15 inches. Find the side length of the square base. So remember, volume, this is pyramid, 1/3 area of base times height. Our basic goal is, see, it is a square pyramid. So as far as that goes, I'm going to kind of like rough it out. Boom, 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 boom. Here's our terribly drawn square pyramid. We don't know the lengths of either of these things, but we know that they're the same. So I could also write this as, oh, we have the volume, hold on. Well, let me do this. The volume is 60. The height is 15. And the volume, not the volume, the area of the base is an unknown x squared. So as far as what I can do, this is basically going to do a substitution for everything in there. 60 volume equals 1/3 area of base, x squared, times height, 15. We got to solve for x. A third of 15 is 5. Divide by 5, you get 12. Take the square root of both sides. Square root of 12 is also 2√3. So the length of the base, each base edge is 2√3 inches in length. I don't know if that's one that we're supposed to be rounding. If we do, because we've been rounding everything else, right? So let's do that. So 2 times square root of 3. I mean, that is exact, though. So 3.464 inches. So about 3.46 inches. I don't know. It feels dirty with this one being just as exact as it is. But, yeah, we'll do it. All right. Number 25. Another volume. Another square pyramid. This time we're trying to find the height. So the volume is 1,024 cubic inches. It's still a pyramid. The base has a side length of 16 inches. So area of the base 16 squared is 256. This is inches? Yeah, inches. And height is unknown. So this time, volume, 1024, equals 1/3 area of base times height. Does 256 divide by 3? I don't know. I'm going to try and not care because I can divide by 256, and 1024 divided by 256 is 4. So 4 is 1/3 of height. If I multiply both sides by 3 now, I get a height of 12 inches. So whether or not 256 could divide by 3, not my concern. I don't believe it can, but didn't matter. 256 could divide by 1024 could divide by 256, and it all worked out in the end. All right, that is 11.5. Let's move forward. 2 more sections. And still 9 more questions to go. No problems on this side except for the example, so let's see what they want to tell us. Surface areas and volumes of cones. Now, there's an interesting formula here, pi r squared plus pi rl for the surface area of a cone that's completely talking about every facing. Pi r squared is the area of the circular base. Pi rl is the lateral area that you're talking about here, this party hat. We're not going into why this is right now, but L represents the slant height of the cone. The radius of the cone is still this guy here, that 5. That r that you're talking about here is still the r that you're talking about there. Now, they're going to do some rounding for these things. So to find the surface area of the cone, we have pi r squared plus pi rl. We need to, this 12 actually won't be used, not for surface area. The radius is 5. We'll use that, pi times 5 squared. And pi times 5, radius times L, slant height is 13. You combine everything, the pi's combined, you get 90 pi, and approximated, you get 282.74 square centimeters. That's surface area. It is square units. Then they find the volume. Volume of a cone is like the volume of a cylinder. The volume of a pyramid is 1/3 area base times height, where it's like a prism. The volume of a cone is 1/3 area base times height, like 1/3 of the volume of a cylinder. So we have to find the area of the base times that height, take 1/3 of it. Now the height this time is 12. We will be using that. So area base 25 pi times that height of 12, and 1/3 of that gives you 100 pi, which rounds to 314.16 cubic centimeters. So let's move forward into their problem set and let's find some cone volumes, shall we? Or surface area. We got to do both. Number 26. So for surface area, let me write this up here. Oh, don't want to bring it with me. Surface area is pi rl plus pi r squared. I always write it differently than they do. I focus on the pi rl a little bit more because sometimes in composite figures, which they haven't done any of these of, sometimes that base area can be covered. And I really want to emphasize the lateral area first. This is the lateral area plus the base area. So the radius is, for number 26, 9 centimeters. We don't have the slant height yet. So we need to find that. The slant height is going to be found by using Pythagoras. Oh, yes, we do. It's 15. I'm sorry. I didn't see that. But we could have found it. See, they don't need to give us that information. We can find that. We can use 9 squared plus 12 squared equals that one, L squared, and we can use that to find the 15. They help us, I know, but then they give us more information than we need, which technically I guess the example problem did, and I wasn't paying attention. So the surface area is pi. The point is, if you're tested, this is a review. If you're tested on this stuff, you got to make sure you know what to do for yourself, because if they don't give you all the excess information, make sure you're hearing me on that. Okay, 9 times 15 is 135 pi, plus this 81 pi here. So as an exact answer, we're getting 216 pi square centimeters. This is surface area. As an approximated answer, probably in the 675 range, I don't know, 216 pi, 678.58. 678.58 square centimeters. Okay, that's surface area. We still do need to find volume. The height of this guy, my calculator's covering it, 12 centimeters. So the volume is 1/3 area of base. Did we find? We did, 81 pi. 1/3 of area of base times height. Let's do 1/3 of 12 to get 4, and 4 times 81 is 324. So 324 pi cubic centimeters. That one, I think that should exceed 1,000. 324 pi. 1,017.88. 1017.88 cubic centimeters. So surface area volume, we're going to do it for every problem in this set among those three sets. So there's the first one. Okay. All right, let's go to the second one, number 27. And on number 27, we got, again, excess information. By the way, this is part of a 3, 4, 5 triangle set. This is part of the 8, 15, 17 triangle set. Everything's doubled. And hey, this time they're going to make us find it, and this won't be part of a Pythagorean triple. Okay, but number 27. We have, let's just write the things out right now. The radius is 16. The height, not part of surface area, is 30. And the slant height is 34. As far as surface area goes, we're going pi RL. Pi RL. Probably going to let the calculator help me. Plus pi r squared. I know that's 256 pi. That's, I'm going to say 544 pi. Let's see if I got that one. Yes, 544 pi. 544 pi. Ooh, this looks like a clean addition. That looks like 800 pi on the button. 800 pi square centimeters. So that's exact. And rounded, get probably around 2,500. 2,513.27. 2513.27 square centimeters. There's your surface area. Le volume is 1/3 area of the base we had there times, I still don't know if I can, you can't divide 256 by 3. It's 85 point something. 85.3 repeating. Times the height of 30, but thankfully I can take 1/3 of 30, which is 10, and 10 times 256 is 2560. So you get 2560 pi cubic centimeters. It should be over 8,000. 2560 pi 8,042.48. 8042.4. Whoops. Well, I can try that. 48. There we go. Cubic centimeters. Yeah, lots of big old numbers and kind of lots of work to do within individual problems, and I hope it's kind of working itself out the way that you try that, right? I hope you try the solution guide videos by saying, I'm going to pause you, Mr. Robinson. I'm going to try it for myself, and if I get stuck, I'll go to you, and after I get my answer, I'm going to check and see if I got it right. If I got it wrong, I'll work on it. If you're learning as you go, great. But we've done two problems that are the same. This one's similar-esque. We have the radius. We have the slant height. What we don't have is the height. This problem's different because we don't have the height. And this is the first one where it's not going to be a Pythagorean triple. We're going to have an approximated answer. Well, I'm going to leave a square root there. It's not an integer. So, that's not the hypotenuse. H squared plus that. So the height is, this guy. So h squared plus the radius squared, which is 7, equals 13 squared. Let's see where we're going with that. Not a bad number. 120. So the square root of 120. Well, let's at least simplify that a little bit. 4 and 30. I guess just 2 root 30. I guess you can't get much cleaner than that, but that's kind of an exact value, if you will. The surface area, there's the information. Let's kind of break that apart. Surface area, we still got to find pi RL. So our original values, we actually didn't need height for this, just for volume. So pi, that's 7, RL plus pi r squared. 7 times 13 is 91. 91 pi plus 49. Pi is 140 pi. I'm going to say that's under 450. Let's see. 140 pi. 439.82. Oh, this is what? Meters? Square meters. 439.82 square meters. So there's our surface area rounded to the nearest hundredth. Le volume, 1/3 area of base, that's the 49 pi, times our height, that's the 2 root 30. So that's where that part's used. I'm going straight into the answer here. I don't think anything here can divide by 3. And so I don't know what it's going to round to even close to. Your guess is as good as mine. I'm telling you what. 2 root 30 times pi. Oh, I already have pi. Divided by 3. Divided by 3. 562.10. You might wonder why I put the 0. If we're rounding to the nearest hundredth, you want to keep that precision intact and just emphasize the fact that it is a 0 that trails. It's just as significant as any other number there. It's letting you know specifically what it's going to be. So I'm writing that one out. Okay, so there is number 28. That is the volume surface. I mean, that took a lot of work because we had to do a lot of things within those and 2 things in each problem. We still have number 29 to do. And on number 29, they say a cone with a diameter of 16 centimeters. I might draw this out. Has a volume of 320 cubic centimeters. Find the height of the cone. I won't draw it out. The diameter is 16 centimeters. You know that radius is used in all this stuff. We got to divide that by 2, and we get 8 centimeters. Now let's work off of how that would be useful, right? This is a cone. We do 1/3 area of base times height, and area of base is a part of it. So pi r squared, which is 64 pi square centimeters. So find the height of the cone when we have volume of 320 pi cubic centimeters. So the 320 pi, and this is in terms of pi, right? 320 pi equals 1/3 area of base times height. So if everything worked out the way that we need to. Can 64 divide by 3? No. Does it matter? No. I'm going to divide both sides by 64 pi to start with. Because can 320 divide by 64? I think so. I think you get 5. And the pi's divide as well. So this really cleans up. This is 5 equals 1/3 of h. Multiply both sides by 3. Your height is 15 centimeters. There it is. No calculator necessary. No terms of pi, or no multiplying by pi, things like that. Okay, there's that one. We have one more section to go. I believe 5 more problems. Section 11.7, surface areas and volumes of spheres. Everything we see fits on this one portion here. Before we hit number 30, let's take a look at what they want to talk about. Surface areas and volumes. Different kinds of formulas here. Whoops, don't want to write anything yet. Let's start with their examples. Find the surface area and volume of the sphere, part A, part B. Now, surface area of a sphere is 4 pi r squared. If you've seen a baseball unwrapped with leather, you can think of it as the area of the 4 circles of them. Your radius is 18, so 4 pi r squared. Listen, it's just a calculation from there. You got that number. We'll do the same thing in terms of speed. I just got to punch them in the calculator. So do you. Volume of a sphere is 4/3 pi r cubed. That's a lot of stuff to kind of take into effect, but if there's only one to memorize, I guess that's it. You say it enough times, I think you'll know it. So 4/3 pi r cubed, same-ish. You plug in 18 as it's the radius, and you calculate, and you get, a big number. Big number in terms of cubic inches. So there are the examples. They make sense. Use the calculator. Go to work. Now, they might do hemispheres. I don't see any here. But they might do hemispheres, in which case you take half the volume. You don't take half the surface area. I'll talk about that if we do them. I did do problems at the time. If we don't run into them here, you can find them in the problem set on 11.7. All right, find the surface area and volume of the sphere. We have a radius of 7 inches for the first one. So as far as surface area goes, it's going to be 4 pi r squared. 7 squared is 49. 4 times 49 is 196. So you get 196 pi square inches. Rounded, it's going to be what, 630, 640 something? I'm going to say 645. Really close to 645. Let's see. 196 pi. Oh, 615. Who sucks now? 615.75. I was very off on that one. Sorry, I must have been thinking something different with my numbers. Maybe I was so close. I was thinking 200 pi. I don't know. Oh, that would have been off. Yes, yes, it would have. All right, volume. 4/3 pi r cubed. Not even going to do anything pre-round. So 4/3 times 7 cubed times pi. Straight up. 1436.76. Rounded. Cubic inches we have. All right. There's number 30. Number 31, this time they give you the diameter. So if the diameter is 17 feet, we got to find the radius. All these have R. All these have R. So diameter is 17 feet. Let's take half of that. Get la radius. 8.5 feet. Let's use the decimal version. So same stuff as before. Surface area, 4 pi times 8.5 squared. Why not go straight into the answer? Now that it's a decimal that we're kind of working that off of. Actually, 8.5 squared, actually, that might be a whole number. It is a whole number. 289 pi. Hold on a second. Let me write that. I'm big on that stuff. 289 pi square feet, which is about... Oh, do I want to guess that? No. It's over 800. I don't know. 900. 907.92. 907.92 square feet. I should have known. That was close to 300 in and of itself. I should have known. All right, volume. 4/3. This one I'm going to go straight into it. Pi times 8.5 cubed. Probably like, you're holding up the video by trying to guess numbers. Hey, you know what? You don't have to watch me. 4/3 pi. This is me keeping myself engaged. Keeping my brain fresh. Otherwise, I lose this ability, I'm telling you. When I hit summer mode, oh, I lose it so bad. 2572.44 cubic feet. It really needs to come back, dude. I get in full softball mode and watching baseball and stuff like that. Not doing math. I don't do math unless I'm making videos. Guys, I don't know if other math teachers are geeked out and stuff like that. Like they just spend time doing math videos. I gotta fully admit, guys, I don't do a lick of math over the summer unless I'm teaching it. It's not a hobby. All right. Circumference. Okay, so circumference is 30 pi feet. Now we want to find radius, right? Same thing. Circumference is 2 pi times your radius, so 2 pi r. So to find radius, you divide by 2 pi, right? We divide by 2 pi. So this is where, the pi's cancel and 30 over 2 is 15. So your radius is 15 feet. This is feet? This is feet. Radius is 15 feet. So let's go to the things as we saw before. Surface area is 4 pi r squared. 15 squared is 225 times 4 is 900. So 900 pi square feet. 2750. 2752. Let's see. 900 pi. 2827. I gotta lay off the non-calculator. 2827 point. I lost it at the end. Square feet. All right. Let's move this over a little bit. The volume. At least I haven't seen the answers before. Volume. 4/3 pi times 15 cubed. Listen, this actually has an exact answer to it because 15 is divisible by 3. Let me find that out first. 15 cubed divided by 3 and then times 4. 4,500. So this is 4,500 pi is an exact answer. I kind of like the look of that, so I wanted to write it out. Times pi. Let's just see what it is. 14,137.17. Let me make sure I wrote that number right. 14137.16. Yes. Okay. All right. So there is volume surface area of that particular sphere. We got 2 more problems to do. How long have we gone? We got over the hour mark with my calculations. Numbers 33 and 34 remain in the sphere business still in some way. The shape of Mercury can be approximated by a sphere with a diameter of 4,880 kilometers. Find the surface area and volume of Mercury. So it's no different than the other problems. We just use kilometers instead. We start with diameter, and I think we did from another problem as well. So, okay. Diameter is 4880. It's just they're using real world things. So if I go and like Google this answer, which I kind of feel inclined to after, we'll say, how close was it? Of course, we are approximating. It's not exactly a sphere, and it's not exactly this diameter. So half of this, but I think they like to flex that we're using real things muscle, and this is how you can do it. So I want to try it. So the surface area of the Merc is 4 pi r squared. I won't dare write the exact. It's just too big to care. But we are going to write the rounded. So let me use my calculator, which I wouldn't know the answer by approximating. 2400 squared times 4 times pi. All right. Okay, big number. So 748,15144. It has the 0.09. I'll be honest, I think normally with these kinds of problems, they really don't care about that extra 900ths of a square kilometer. This is 74.8 million square kilometers. So I'm just going to write it like that. They might have said to the nearest square kilometer. No, they didn't. Volume. 4/3 pi times this cubed. Number's going to be even bigger. All right. 4/3 pi times 2440 cubed. Okay, so my calculator does a scientific notation hassle, and I don't want to mess it up, so I'm going to do this again on this other calculator that'll give me a bigger number. Times, where's pi in this calculator? Give me 1 second. There it is. Pi times 2440 raised to the third power. All right, so this number is in the billions. It's a 60 billion number. So 60 billion, 849,650,526 cubic kilometers. So if we Google this thing and ask it, it'll probably say around 60 billion cubic kilometers for volume. I'm curious. I'm going to Google these things right now. What is the surface area of Mercury? They say 28.88 million. Oh, in square kilometers. In square kilometers. 74.8 million square kilometers. We have that 74.8, right? So cool. Let's do volume. So what do you think we're going to say? 60.85? What is the volume of Mercury in cubic kilometers, I guess? They say 60.8 billion cubic kilometers. So yeah, obviously they work off maybe that data and then they do it. Look, they're math nerds. They're going to find that information pretty easily and they can work it out that way. Perfect. I like they use real world data. Good. All right, last question, number 34. A solid is composed of a cube with a side length. Oh, okay, perfect. We get to actually talk about composite solids and use all this. Perfect. A solid is composed of a cube with a side length of 6 meters. I'm going to draw this. And a hemisphere with a diameter of 6 meters. Find the volume of the composite solid. So it's like a planetarium. It's like a building with a dome on top. So I'm going to try and draw this best as I can because I'm not good at this stuff here. All right, that's the hemisphere in that this is broken up like that. So we have kind of this going on. Good enough. Okay. I got a cube and a hemisphere. All right. So the cube, that looks ugly. The cube has a side length of 6 meters. Now it's a cube. Everything is 6 meters there. The dome right here is a diameter of 6 meters. That means it's like tangentially touching the square, that kind of stuff. Find the volume of the composite solid. So the volume of the composite solid, listen, there are two figures. There's figure 1 and figure 2, whatever you want to call it. I'm going to find the volume of figure 2 first. That's 6 cubed, which is 216 cubic meters, straight up. Oh, do we need just the volume? Okay. If we were talking about surface area, which actually, never mind. Surface area would be a lot to talk about. I'm not going to talk about it. The volume of object 1, the hemisphere, is half the volume of a regular sphere. Instead of 4/3 pi r cubed, it's 2/3 pi r cubed. Now the radius, let's do that. The diameter is 6, so the radius is 3, right? So 2/3 pi times 3 cubed. And listen, I have an exact value I can do off that. 3 cubed is 27. A third of that is 9. 9 times 2 is 18. So you get 18 pi cubic meters. So the volume of them together, we add them both. The volume of the total, we're going to do the V2 plus V1, like that. And we jump straight to the rounded. Why not? 216 plus 18 pi. 216 plus 18 pi. 272.55. 272.55 cubic meters. The volume of the composite solid. And guys, that should do it here. This was Chapter 11 review, and it's the last review that we have in the textbook. I mean, we're going to do a chapter test and cumulative assessment, stuff like that, but this is the last chapter, and the last chapter review with that as well. So that'll do it for this one. This is Mr. Robinson. Thank you so much for watching, and take care. I will see you in the next one.